we'll be learning about competency number 5.2. What is there in this competency? We learn the properties of cardiac muscles. It has got different types of properties. One is electrical, another is mechanical, and other were morphological and metabolic properties. Means they are having certain characteristics, morphological characteristics. First, we'll see what are these morphological characteristics. Cardiac muscle cells are involuntary and striated. When you will be observing under the microscope, you will find striations. And these striations are due to presence of contractile elements, that is actin and myosin. Each muscle fiber, what is the size of this muscle fiber? They are 100 micrometer in length and they are 15 micrometer in broad, and these cells are bounded by sarcoplasm. Though they are bounded by sarcoplasm, they are connected to other myocytes, cardiac muscles, by intercalated discs. So there you will find, when you will be studying the cardiac muscle cells under microscope, you will find they are freely branching and they are connected to each other by intercalated disc. What is there in the intercalated disc? There is presence of desmosomes and gap junctions. What is the purpose of connecting the cardiac muscle cells together? What is the utility? Means all the cardiac muscle cells are to function together, work together, so that all the muscle cells can generate force. Because this force will be requiring to pump out the blood from their cavity into the circulation. So for generation of these forces by the cardiac muscle cells, so they must be connected to each other through gap junctions. If gap junctions allow transmission or there is connectivity, so suppose this is one cardiac muscle cell, these are connected, another cell, so they are connected by gap junctions. So if I apply one stimulus, apply a stimulus to this muscle, it will be communicated to all the cells because all are connected together. Impulse can be, and the movement of these are low resistance. There is low resistance channel, so through these channels easily ions can move from one. For generation of cardiac impulse, for generation of force, so this action potential should reach to all the cells. Okay, so for this purpose it is needed. Moreover, okay, so these cells should be tightly adhered to one another. Otherwise, the cells may become splatted. So they should be tightly bound to one another, and this is done by the desmosomes. So desmosomes is performing these functions and the gap junctions are performing communication. So if you stimulate one cell, all the cells, if they are connected by gap junctions, all the cells will be contracting together and lot of force they will be able to generate. Okay, so that's why they are interconnected. And moreover, these cells, you find they are highly vascularized. Why highly vascularized? Because they are working continuously without any gap, without any rest. So for this purpose, for this work, they must have adequate supply of nutrients and adequate supply of oxygen and removal of waste from the cells. That's why lot of vascularity must be there. In 1 gram of cardiac muscle, they get 3 ml of blood per minute, whereas the cardiac muscles get through these capillaries 80 ml of blood per minute. So that's why this such difference, because the cardiac muscle cells are highly vascularized. Only vascularity will not do. You will be supplying oxygen and supplying nutrients. This will not do, because oxygen, what is the purpose of oxygen? Oxidizing the metabolites to generate ATP. What are the mechanisms that the cells are having for generation of ATP? Mitochondria. So that's why these cells are having lot of mitochondria, and they are having also lot of glycogen stored in their sarcoplasm. Okay, so these are another features of the cardiac muscle cells. Cardiac muscle cells work as a syncytia. Syncytium, singular, syncytia, plural. What is syncytia? When a group of cells work together. So we can see the cardiac muscle cells, they work together. If I stimulate one, all the cells will be getting the stimulus and they will be contracting together. So functionally, they work together. Now, all these cells are, so we can see in heart there are 2 syncytia. Can you name them? One is atria and one is ventricle. When both these syncytia, atria and ventricle, they are separated from one another by fibrous tissue, and these fibrous tissues are present in between the atria and ventricle, and this fibrous layer actually differentiates atria from the ventricle. Only one communication is there. Only one source of communication is there between the atria and ventricle. Otherwise, atria cannot communicate its electrical or action potential to the ventricles except this route. What is this route? Bundle of His. It is bundle of His. Through this bundle of His, ventricle gets impulse from the SA node. AV node also there in right atrium. So SA node to AV node is the atrium. So from AV node, it is passing through this junction. Junction means this fibrous layer. It is passing through this fibrous layer. So there is what? Bundle of His. So now from AV node, it will be passing through the bundle of His. Then this impulse will be transmitted throughout the ventricles. Then ventricles will contract. Okay, so we can see atria, when a stimulus will be there in the atrium, all the atrial cells will be contracting together, not the ventricular muscles. Because ventricular muscles not yet receive the stimulus produced in the SA node. Why? These are delayed. The stimulus is delayed in the AV node and bundle of His. After completion of contraction of the atria, then only ventricular muscles will get the stimulation and it will contract. This is necessary. Why this is necessary? When atria contract simultaneously, if ventricle also contract, then how, if ventricle is contracting, it is contracted, then atrium is trying to send its blood to the ventricle, but how it will enter within the ventricle? Not possible. So, atrium has to receive the blood, then it is to contract. Now the blood will be going to the ventricle, then only ventricle will be contracting. So there must be a pause between the two. And this is, for this reason we call the heart is having two syncytia. One is atrium, another is ventricle. Is that clear to you? Fine. Cardiac muscle are of two types. One is working cardiac muscle. Means if you stimulate this muscle, they will be responding by contracting. And another type, if you stimulate it, or they can produce their stimulation, own stimulation, and this stimulation is conducted through those tissues. What are these tissues? Junctional tissues or conductive tissue. Their function is to conduct, either to generate the impulse and to conduct the impulse to the working muscles. So when this impulse is transmitted to the working muscle, then only ventricular muscle will contract. Okay, so these are the some properties, and this another difference is that microscopic and electron microscopic structure of skeletal muscle, cardiac muscle is very same, as almost same to the structure of skeletal muscles. The cardiac muscle cells are highly vascular, as I said. There are plenty of cytoplasm, glycogen and mitochondria in the cells. T-tubular system penetrates sarcolemma at Z-line. In skeletal muscle, you will get two T-tubules in one sarcomere. But in case of, this is another difference, in case of cardiac muscle cells, per sarcomere, you will get one T-tubule. So there is one triad per sarcomere. So these are the intercalated discs, one nucleus. These are the striations. These striations are because of actin and myosin. And this intercalated disc, this is the structure of the intercalated disc. These are the desmosomes. These are desmosomes, and these are the gap junctions. Now we will discuss about the electrical properties of cardiac muscle. Three main electrical properties the cardiac muscles are having. These are, one is excitability. What do you mean by excitability? Can anybody tell me? What do you mean by excitability? These are not excitable. These are excitable. When we apply a stimulus, what will happen? The cells will respond. Cardiac muscle will also have excitability, but their way of responding is since all the cells are having, all the living cells are having transmembrane potential, means resting membrane potential. Now when you apply the stimulus, there will be change, reversal of resting membrane potential. As a result, there will be development of action potential. So cardiac muscle also, when they get stimulation, they will be responding by making reversal of resting membrane potential, that is production of action potential. So they slow type action potential, another is fast type, fast type action potential. We will discuss now what is slow type action potential, what is fast action potential, where we will find these two types of potential. Slow type of action potential you will find only in pacemaker cells. What are these pacemaker cells? SA node, AB node and bundle of His. They are the pacemaker cells. These cells are capable of producing slow action potential. But other cardiac muscles, working cardiac muscles, they can't produce slow action potential. Instead, they produce fast action potential. So you will find fast action potential in working cardiac muscle and slow action potential you will find in pacemaker cells, that is in SA node, AV node and bundle phase. Okay? And we know SA node, AV node, bundle phase, they are capable of producing cardiac impulse by their own. It is because of this slow action potential. It is because of slow action potential. Actually, slow action potential is nothing but generation of cardiac impulse. So, slow action potential are actually cardiac impulse. And this cardiac impulse is generated because of one property the acinodal cells are having. What is this? They can generate pacemaker potential. They can generate pacemaker potential. We will discuss about what is spontaneous production, how there is production of spontaneous production of this slow action potential. So this is fast action potential. This is fast action potential. Seen in what type of cardiac muscle? Working cardiac muscles, mean atrial muscles. After getting this impulse, when these working muscles get impulse from SA node or AV node or bundle phase, they will also produce action potential. And when this action potential is produced in these cells, the muscle will contract simultaneously. When these are generated, this fast action potential is generated in working muscles, so we'll find from there calcium ion is liberated. Calcium liberated means they are entering within the sarcoplasm. And we know for contraction of the muscle, calcium ion is needed. So when the calcium ion enters here within the cell, then only contraction starts within the mitochondria, within the muscle cell, and the contraction will be finished at this point. Okay, now the cell is ready for another contraction, means another action potential, to get another action potential and to produce another contraction. During every action potential, calcium ion is liberated, and this calcium ion will cause contraction of the muscles. Now see, suppose this is the cardiac cell, working cardiac cell. So cardiac impulse generated from SA node, it is traveling to this cell. This is the surface, and they will enter, this action potential will enter into T tubule, and when this action potential will be entering into the T tubule, and it will cause opening of calcium channel, and as a result calcium ion will be released into the sarcoplasm. Now excitation, contraction, coupling will be initiated, muscle will be contracted. Okay, so how this action potential is generated? So here the cell, this is the time, so here the muscle got the stimulation. Then what happened? Permeability to sodium ion increased. Working cardiac muscle, stimulation it received. Now there will be release of calcium ion into the sarcoplasm. Now actin myosin will form cross-bridge and this will be contracted. Now, how these cells are stimulated? Outside is positively charged, inside is negatively charged. When the membrane got stimulation, what happened? Here, sodium channel opened. There are different types of sodium channel. One is leaky channel. Through this leaky channel, entry of sodium ion from outside to inside is slow. And there is another type of channel, voltage gated sodium channel. This is one type, leaky channel. Another is leaky channel. Funny sodium channel. And ligand gated sodium channel. When ligand binds to their receptor, the channels, ligand gated channels, suppose this is the sodium channel. So there are pentamers. So one of the pentamer is acting as receptor of the ligand. When the this receptor binds with the ligand, what is happening? What will be happening? There will be conformational change in the protein. So this channel will be open. Now the sodium can enter. So these are ligand gated sodium channels. And voltage gated channel, when the inside of the cell, the potential difference is such that inside has become say minus 40 millivolt. Now what will happen? Lot of sodium channels will open up. So outside sodium concentration is much high. So sodium ions will be entering within the cell and there will be rapid change in membrane potential. It will develop. So same thing is happening here. When sarcoplasm is stimulated, sodium channels are opened. Leaky channels are opened, so slowly sodium ion is entering. When it has attained the threshold level, this is the potential difference. When it attained the threshold level, then only what happened? Lot of voltage gated channel opened. Now there will be rapid entry of sodium. Because of this rapid entry of sodium, there will be depolarization, means potential change towards positivity. So it will rise. Voltage gated sodium channel, it is such that it has two gates. One is activation gate, another is inactivation gate. And these gates are once open and very shortly they will be closing. Very shortly they will be closing. So within this, since lot of sodium channels are open, so lot of sodium ion will be entering within this short period. So here what happened? Sodium channels, voltage gated sodium channels opened, lot of sodium ion entered within the cell. As a result, there is potential change up to plus 35 millivolt. You may ask, sir, why not 45? Why not 60? Because sodium cannot enter because the inactivation gate, activation gate, they are now closed. Sodium channel is now closed. We told you for certain period of time, this will remain open. Now, these are closed, so there will be no entry of sodium ion. Okay. So, this will make, this phase of depolarization is called zero phase. This phase is called zero phase. Now, when is attained this plus 35 millivolt, at this condition, within the cell, the potassium channels open. Potassium ion concentration is more here within the cell. Now potassium ion will come out. At that point, at this point, at the peak, potassium channels open. Now potassium ion will be coming out. If potassium ion comes out with its positive charge, what will be? Inside will become more negative because positive charge is going out. So inside will be more negative. That's why potential is falling. So this phase 1 is due to exit of potassium ion. Phase 0 is because of entry of sodium ion, and phase 1 is due to exit of potassium ion from inside to outside. We call it efflux of potassium ion. Now what happens? The resting membrane potential becomes plateau. It becomes plateau. There is no change in potential difference. Okay, why this happened? Potassium ion is going out. Potassium ion is going out. At the same time, another channel opened. What is this? L-type calcium channel. L stands for lethargy. Lethargic channel. It opens slowly, closes slowly. It opens slowly, closes slowly. So as a result, opening of this L type of calcium channel will cause entry of calcium ion within the cells. Now, entry of calcium ion, amount of calcium ion that has been entering will be the same amount of potassium that is outgoing. As a result, the voltage will remain same. This amount of entry of amount of calcium ion within the cell is equal to the amount of exit of potassium outside the cell. As a result, we get this plateau phase. So what is the reason of this phase 2? What is the reason of phase 2? What is the cause? What is the ionic basis? Entry of calcium ion and exit of potassium, and rate of entry of calcium ion and rate of exit of is same. That's why the potential is doesn't change. Okay. Thereafter, what happens at this phase? At this phase, what happens? Calcium channel, that L-type calcium channel closes, but potassium channel remains open. Now, no sodium or no calcium ion is entering. Only potassium is going outside. As a result, what will happen? The cell will become gradually negative. Cell will become gradually negative. That means there will be repolarization. So, change in potential from towards negativity is called repolarization. Change in potential towards positivity, towards positivity, towards zero or positivity is called depolarization, and change in potential towards negativity is called repolarization. So this is the phase 1 is the initial part of repolarization, and this is caused by exit of potassium ion, and phase 2 also steady, it is not depolarizing, it is maintaining a steady state. And why this? Entry of calcium ion and exit of potassium ion remains same. But after some time, calcium channel closed. So thereafter, what will happen? Only potassium ion will be coming out. So there will be repolarization. Change in membrane potential towards negativity. So you will find phase 3. So this is called phase 3. And when this potential difference comes to the resting level, which is 80 millivolt. In case of working muscle, it is 80 millivolt. So it has started developing depolarization from 80 millivolt, reached to plus 35 millivolt, and this plateau phase you saw near about at 0 millivolt, and thereafter repolarization started from that point up to this level. This is minus 80 millivolt, and this is phase 3 caused by potassium ion, and this is now phase 4. Potential at resting level is called phase 4. So how many phases are there? How many phases are there? 4 or 5? 5. 0, 1, 2, 3, 4, 5. So do you know what are the reasons of this? Now what happens in phase 4? Lot of sodium ion has entered. These are now trapped within the cell. Lot of potassium ion which was inside, they have gone outside. They are trapped there. Lot of sodium ion, calcium ion has entered within the cell. They are trapped there. Now what to do? So during the phase 4, now they will be redistributed. Sodium ion will come out, potassium ion will enter, and the calcium ion also go out. How? By 3 mechanisms. One is sodium, potassium, ATPase pump. They will cause redistribution of ions, sodium and potassium ion. And another exchanger is there, that is sodium calcium exchanger. And there is another pump, sodium calcium pump. So using these 2 pumps and exchanger, all these ions, these 3 ions are again redistributed to their original position in phase 4. So what is happening in phase 4? What is happening in phase 0? What is happening in phase 1? What is happening in phase 2 and what is happening in phase 3? You understood this. Is that, am I right? Okay. Now you have seen this type of action potential where in the working cardiac muscle. Let's see what happens in slow response action potential. In slow response action potential, you will miss phase 1 and phase 2. Here you won't find phase 1 and 2. Phase 1 means downward, means caused by the potassium ion, and the plateau that you won't get. There will be phase 0, there will be phase 4, there will be phase 3. Only these phases are there in slow type action potential, and this is very important for generation of action potential, cardiac potential by the acinodal cells. In acinodal cells means pacemaker cells. These pacemaker cells, their membrane is unique. They are having some channels which are unique, and because of these channels, these cells can develop their own cardiac impulse. And because of the presence of these channels, you won't find any resting membrane potential. You won't find any action. The resting membrane potential is not at all resting. Whenever the potential comes to the resting level, immediately it undergoes depolarization. So no resting. And this property of these cells make it special from other cells, and for this property it can generate its own impulse. Let's see how. This is one action potential. When this is the repolarizing, phase 3, repolarizing means calcium ion is going out from cells to the outside. When it is coming to this level, then what happens? Some sodium ion starts to enter, and this is very funny thing. Why this is funny? Usually sodium channels open during depolarization. But here I can see some sodium ion channel, they open during repolarization. And you won't find this type of thing in any other cell. This is present only in P cells, pacemaker cells. That's why it is called funny sodium channel, funny current, and it is represented as IF. It is represented as IF. I station current, the flow of current from outside to inside, done by entry of sodium ion. So this is during repolarization. This sort of entry is funny. We know sodium channels only open during depolarization. So this sort of opening of this sort of calcium ion is not usual. That's why term is given as funny current. What is the cause of the funny current? Entry of sodium ion during repolarization. Now, because of this, the repolarization, sodium ion is entering and potassium ion is going out. So here what will happen? Potassium channel will be closed. Only sodium ion will be entering. As a result, again there will be depolarization. Again there will be repolarization. Again there will be depolarization. So first part of this depolarization is done by the funny current, IF. And the second part is done by, here what will happen? Instead of together with sodium ion, entry of through funny channel, there will be entry of calcium ion. There will be entry of calcium ion. So sodium ion is entering, calcium ion is also entering as a result, and this calcium channel is transient. They will remain open for a while, only for a short while. Okay, so because of this, some amount of calcium ion will enter and will make the potential. So what this potential from -60 to this level, this is the threshold level, -40. This is -40. So change of potential from -60 to -40 up to this. This part of depolarization is called pacemaker potential. This part is called pacemaker potential. And this is unique for acidoidal cells. And why this potential change has been made? Funny current and calcium entry by transient channel, transient T-type, transient type of calcium channel. Okay, so who are the responsible for phase 4? Two factors. At the initial stage, I current means funny current means sodium entry, and the later part of pacemaker, this pacemaker potential, this part is entry of calcium ion by the T channels, transient channels. When this potential difference came to the threshold level, then what happened? Another type of calcium channel opened. That very L type of calcium channel, lethargic type of calcium channel. Now calcium channel, L type of calcium channel open, so there will be lot of calcium ion, and this calcium ion is responsible for changes in potential during zero phase. In that case, who are the responsible? Sodium ion, atria of sodium ion in working muscle. Here, who are the responsible? Who is the responsible ion? After threshold, calcium ion entry. In the previous case, where there are 5 phases, the zero phase is done by the entry of sodium ion through voltage gated channels. Here, L type of opening of L type of calcium channel, entry of calcium. So this is done by only entry of calcium ion. So now this channel will be closing here. ICAL, my L type of this channel closes here, and another channel will open now, the potassium channel will open. So no entry of calcium ion, no more depolarization. Now potassium is open, potassium channel is open. Now potassium will be coming out of the cell, and this will be coming gradually. Potential will become negative gradually. When it's coming to this way, when stage 3 started, here the potassium channel will close and the funny current will will be entering, or that is sodium ion will be entering. So this way pacemaker potential is developed, and this pacemaker potential causes development of cardiac potential or action potential, slow type of action potential. Could you make the difference between the two? Okay. So these are the difference between fast response action potential and slow response potential. What happens during it? What happens? See, phase 1, phase 2 is absent in case of slow response action potential. Here both are present, and what are the causes? These are illustrated here. Cardiac muscle has got another property, that is conductivity. Whenever you give a stimulus and a stimulus, a potential is developed in SA node, and this potential, that is cardiac impulse, will be conducted to the ventricular muscle or to the auricular muscle. When the auricular muscle gets this impulse, it will be contracting. When the ventricular muscle gets this impulse, they will be contracted. So this impulse produced in the SA node or AB node or in the bundle of leaves, they should be conducted to the working muscles. So this property is called conductivity. Okay. So this has, I will not elaborate this because this is already been in our earlier class, we have already discussed. One thing here I want to elaborate. What is this? SA node at right atrium, it produces the impulse. Now it will be circulated through this impulse will be circulating or transmitting to the atrial muscle first. So there will be contraction of the atrial muscle. But this impulse not yet transmitted to the ventricle because of delay in the AB bundles, AB bundle of his. So when this atrium finishes its contraction, then only ventricle will start its contraction getting this impulse. Okay. So first in the ventricle, this is the septum. This part, left side, will first get the impulse. Then it will send the impulse to the right side. So current is cardiac impulse is coming from this direction to this direction, and this way ultimately it will reach the apex. When this apex, it will reach to the apex. When it reaches to the apex, then from the apex it will travel towards the base of the ventricles. So this part is the last part of this part gets cardiac impulse last. And who gets among the ventricle? Which part gets the impulse first? Septum. And who is the last? Base of the ventricle. It takes time. Near about 0.20 second. 22 second. From here to impulse to travel here, it takes 0.03 second. From here to reach here, it takes 0.22 second. Conductivity. So, rate of conduction of cardiac impulse, highest in Purkinje fibers, 4 meter per second. In atrial muscle, it is 0.3 meter per second. In junctional, in SA node to AB node, there are paths, 3 paths, internodal paths, they are having 1 meter per second conductivity. And in AB node, it is 0.05. In bundle of his 1 meter per second, Purkinje fiber up to 4 meter per second. And in ventricular muscle, it is 0.03 to 0.05 per second. So conductivity of cardiac muscles are different depending on the tissues. Mechanical properties. Here you will get 3 contractility. So if you apply stimulus, the muscle will be responding by contraction. Generation of force. So this is contractility, and it is having long refractory period. What is long refractory period? It is about this period from threshold level to the time up to 1/3 of this repolarization. So this will be the 1/3. So this period is called refractory period. Refractory period starts from threshold potential. When threshold potential reached, that is the time beginning of refractory period. When it will end? During repolarization. When repolarization comes to 2/3 of repolarization, reaches 2/3 of repolarization, this much time, about 200 millisecond. 200 millisecond, this is the time. And this time is very important. Why this time? And because of this long refractory period in working muscle, we know cardiac muscle is not fatigued. It is working repeatedly, contracting repeatedly. Though it is not, even then it is not fatigued because of this prolonged refractory period. And all Nanner says, or in refractory period, what happens? Here calcium ion enters within the cell. Now this calcium ion starts EC coupling. Now the muscle is contracting. If you apply another stimulus during this contraction phase, muscle will not respond because it has not yet completed its contraction. It got stimulation first, then it has started the contraction process using the calcium ion. So unless it is finished, it is not ready to take second stimulus. So here only when it has reached the 1/3 portion, here only if you apply a second stimulus and if it is very strong, then only these muscle cells can be stimulated again. Okay, but by this time lot of contraction has been made. Almost the cardiac muscle completed its contraction. So now it is ready for the second contraction. In skeletal muscle, it is not like that. You have performed one experiment, I think, one group, tetanus, study of tetanus. What happens when you give repeated stimuli, muscle becomes fatigued, but that is tetanized. But cardiac muscle is never tetanized, never fatigued. Why? Because of this long refractory period. Refractory period is divided into absolute refractory period and relative refractory period. Absolute refractory period means during this period, if you apply second stimulus, whatever be the strength of the stimulus, it will not be responding because that time the muscle is contracting. It is not ready to take another, not ready to perform another contraction unless it is finished. But if you apply the second stimulus during the absolute refractory period, I said absolute refractory period starts from this 2/3 portion to this portion is the absolute refractory, relative refractory period. So if you apply second stimulus during relative refractory period, this cardiac muscle can respond. So this is called refractory period. Automaticity, automatic production of cardiac impulse, that is done by slow phase, as I already told, and this production is phasic. One production, another production, another. The time between the two productions remains same in all the beats. That's why it is rhythmic. So that is the cause of rhythmicity. All or none law. It is very simple. If you apply a stimulus, and if the stimulus is sufficient, means of threshold limit, then it will produce an action potential. If you give a stimulus of more strength, same result you will get. There will not be any modification in the action potential. If you change the strength of the stimulus, but the action potential will remain same. Not that action, the voltage difference will be from plus 35 to plus 50. Not that. It will be always plus 35. Whatever be the strength, if it is a threshold value, the same response will be made immediately. If it is sub-threshold, no action potential. If it is of threshold limit, action potential will be developed. And if you supra-threshold, Stimulus is or through same action potential will be developed. So this is called all or none law. None means if it is below threshold, then no action potential, and all means whatever the strength over the threshold limit, whatever be the strength, the response will be same type of action potential, same configuration, same type of action potential you will get, same response you will get. And the last point, staircase phenomena or trapeze. What is this? Staircase phenomena, we can make our heart stopped. If you continuously stimulate the vagus nerve, SN node will stop generating heartbeat, cardiac impulse. Okay, now you stop stimulation. Okay, so when heart is stopped, it's beating, it is not dead. It has stopped beating. Now it is called quiescent heart. Now when you withdraw the stimulus, now the heart will start beating. Initially force of contraction will be less, and with second stimulus, contraction will be much more. In third stimulus, it will be much more. Gradually it will increase and come to the normal level. And this is called slow increase in force of contraction in the cardiac muscle in quiescent heart after it has been stopped. So then this type of change is called trapeze or staircase phenomena.